everybody, welcome to Shacktown Falls. Alright, today we're here to collect samples from the water at Shacktown Falls and analyze them to see if it is safe water or if there's something in it that we need to be concerned about. A little bit about Shacktown Falls. It is part of the Yadkin River Basin, so everything within the basin eventually will get fed into the Yadkin River, and this is part of it. This is one of the Yadkin River's tributaries. The falls right now are fairly calm, but they can get pretty big whenever there's a rainstorm coming up. The last rainstorm was a few days ago, so our data should be fairly accurate for a normal day. So as you can see, the waterfall is not a large waterfall. It's actually one of the smaller ones and actually pretty easy to climb. The water here is fairly shallow. The deepest part is about 4 feet deep on a normal day. Some of the features around the waterfall and on the edge of the water. This water source area that we're in right now is very rocky. There's very large rocks in this area. There's some sand and silt that has built up from deposition over time. We have areas where there's been erosion that's carved out sides of the rock. So this part of the Shacktown Falls is very popular for people to come and swim and hang out at. So we do see evidence of people leaving their waste behind, which could be a factor when determining the health of a water system. So some of the things we're going to be analyzing today, we're going to be doing some chemical analysis and also some visual analysis. The things we're going to be looking for are those macroinvertebrates, those organisms that we can see in the water system. The more we see, the more likely a healthy water system this is. We also could look out for larger macroinvertebrates such as crawfish. I have seen some here before. We might see some today. I did bring my chemical water analysis kit. This contains several different components that we're going to use to analyze the water today. We're going to be looking at dissolved oxygen. We're going to be looking at temperature, pH. We're going to be looking at the turbidity. And we're also going to do a separate kit to analyze the nitrates and phosphates in the water as well. So the first thing I'm going to do is actually go collect the water sample into my container. And in order to get a fairly accurate sample, I'm not going to be too close to the side of the water source, and I'm not going to get directly in the waterfall, but I'm going to collect it from near the base of the waterfall. Not where it's really turbulent, but out a little ways. Outdoor science testing area set up. And what I went ahead and did, since it took me quite a bit to get out to where I took my sample because it's very hard to walk on all those slippery rocks, I went ahead and recorded the temperature of the water while I was out there, and it measured at 26 degrees Celsius, which is roughly about 79 degrees Fahrenheit. So for running water, it's still fairly warm because we're still in the summer season, but it felt very, very cold walking out there. So with my analysis, I'm going to be measuring 5 different things. And the first thing we're going to look at is turbidity. And you remember, turbidity is how clear the water is. The more turbid the water, the less clear it is. And the way we're doing that today is with a Secchi disc. A Secchi disc is a black and white disc, and the clearer the disc is, the less turbid the water is. So the Secchi disc is actually in the bottom of my sample cup. And as you can see, we can see the Secchi disc fairly well. It doesn't look perfectly clear though. So what I would compare it to If you look at the options, it looks closest to the 40 JTUs. So we're gonna call it partially turbid. All right, the next thing I'm gonna test is the dissolved oxygen. And to test that, I'm gonna need a glass vial with a lid. And then I'm gonna need 2 of these dissolved oxygen tablets. And depending on what color the tablets turn the water is how much oxygen is in our sample. So I've inverted my sample until both tablets dissolved, and that took about 4 or 5 minutes, and now the directions say we have to let the sample sit for 5 minutes more to finalize the color. So I'm just going to set it right here and set the timer for 5 minutes. Okay, so it's been 5 minutes since our sample started, and now we're going to see what the parts per million results are. And as you can see, it's definitely not clear anymore, which is good. If it was clear, that means there would be no dissolved oxygen within our sample, and that'd be very bad for the water system. So looking at this sample, we can see that it's right around 4 parts per million. It's actually a little bit lighter, but we're going to call it 4. It's definitely not 8 parts per million. So what that means when we look at our chart is we compare the water temperature with our results with the parts per million of dissolved oxygen. And this is going to tell us what percentage of our water is dissolved oxygen. Because remember, the colder the water, the more dissolved oxygen it can hold. So our temperature was 26 degrees Celsius, and our parts per million were 4. So if you look right here, we are 49% dissolved oxygen, which is not great. Part of that is because the water is moving, so it's creating a little bit of turbulence and moving sediment around. And part of it is because it's warmer right now, being that it's still summertime. So in colder water, organisms would be better to survive because there'd be more oxygen. So we may not find as much macroinvertebrates around here that we thought we would. All right, the next thing we're going to be measuring is the pH of the water. And remember, pH is how we measure how acidic or alkaline a water sample is. So we need to see how it compares to our pH chart. And if you remember, the pH of pure water, pure fresh water, should be right around 7. That is a neutral. It's not an acid, it's not alkaline, it's neutral. So healthy water systems will be close to neutral as possible. So let's see what we have. First, I need to collect 10 milliliters of water in my tube. So the 10 milliliter mark is almost all the way to the top. All right, that's right at 10 milliliters. And then it's going to require a tablet like the dissolved oxygen, except this is only one. It actually broke, but that's okay. And then I'm going to put my cap on, I'm going to invert the tube several times until the tablets are completely dissolved. And this should happen a lot quicker than dissolved oxygen. It happens almost instantly. All right, so my tablets have already dissolved. And if you can see, compared to the white of the container, it's not clear anymore. So let's see what our results are. So if you look, our water sample is very, very close, if not exactly, have a pH of 7. So this is a good indication of a healthy water system. That probably means there's not a lot of contaminants floating around that's causing changes in the pH. But we need to do more analysis to make sure that that's not the case. All right, the next two we're going to be focusing on is nitrates and phosphates. And if you remember, nitrates and phosphates commonly come from contamination from fertilizer. And fertilizer can be just straight manure from farm animals, or it can be a mixture of manure and chemicals. And having a heavy load of nitrates in a water system is not healthy. Having a little bit is fine, but having a large amount can lead to overgrowth of plant and algae, and then eventually lead to eutrophication. So let's analyze our nitrates first. For nitrates, I need 5 milliliters of my water sample in a clean tube. So 5 is right there. Okay, that is right at 5 milliliters. So now I need to add 10 drops of solution number 1 to this water. There's 10. All right, now I'm supposed to cap the sample and invert the tube several times to mix the solution. Okay, now it says I need to add 10 drops from solution number 2. All right, and put the cap back on. Now the instructions say I have to shake vigorously and then let it sit for 5 minutes. So let's set the timer. All right, let's see what our analysis showed. So this is the nitrates, and it looks like it mostly resembles tin, which is not great. We actually want it to be as close to 0 as possible. It's not as high as it could be, because it could be up to 160 milligrams per liter. But now we're looking at least 10 and maybe even get close to 20 parts per million when you're talking about milligrams per liter. So there is a significant amount of nitrates in this water, which may indicate that there is some sort of farm upstream that might be contaminating this water. All right, time is up. Let's see what our results are. It's definitely not as bold of a color as the nitrates. But as you can see, our options aren't there either. All right, so looking at this sample, it's definitely on the yellow side. So I would say it's probably between 0.25 parts per million and actually 0 parts per million. It's not quite 0. So we'll just say 0.25 parts per million is pretty close color. I wouldn't say it's as green as 0.5. And this is good because this means that maybe the contamination that we saw with the nitrate levels is not as bad as we think. that there may be just a mild natural cause for the nitrates to increase. And maybe just not a big chemical dump problem in our water system. So this is good news for our water system. Now let's go see what we can check out now that we've done it with our chemical analysis. I'm gonna go see if I can find some wildlife near or in the water system. See if we can spot any macroinvertebrates or vertebrates. There he goes. He went under that flat rock right there. Come on. Don't be scared. I just want to look at you. There. Can you see his claw? Come on. Oh, there we go. Oh, come here. I'm not done with you. That's a very good indication of good water quality. Hi, Mr. Crawfish.
Don't forget. Don't forget.
So we're at the top of the waterfall now, and up here it's basically a big giant rock, and along the waterfall and on top of the waterfall is a lot of this really rough feeling moss. It really helps with the traction up here, but there's a lot of it growing around here, so that indicates that there is possibly a definite increase of nitrates, because even though the water is moving pretty good, the plants are still able to grow quite a bit. And what I'm going to do also is take a water sample home with me. That way I can look under the microscope to see if we can see any microinvertebrates, which are also a good indicator of a healthy water system. Microinvertebrates and a lot of macroinvertebrates cannot survive when there's been changes to water, such as drastic temperature changes or pollution. They are the first indicators that something is wrong. So if you don't find a lot of them, then that may mean that there's something seriously wrong with your water. Somewhere under that water right there is two little boys. We found an underwater cave looking thing. There they are.